Welcome. So our last concept from chapter 1 is the language of graphs. So we mentioned graph theory. So we're going to talk about what are graphs and what's some basic information we can glean from them. So to help understand graphs, let me go through a problem. Suppose I have a group of people and I want to make teams of 3 and I want to order them in a way that they have worked with at least one other person in the group successfully. So as a director, I go and ask everyone who's their previous partners. Well, I get this really cool table over here where Anna has worked with Dan and Flo. So see, I can make a bunch of dots for each of the people, and then I can connect them if they've worked. Because obviously, if Anna has worked with Flo, then Flo has worked with Anna. It is this cool kind of, it goes both ways. So because of this relationship that we have between them. Now, looking at this table, the question is, can I form any groups out of them? And I actually can form some groups. So first thing we might notice is the fact that Flo, Bev, and Kai have all worked together. They have all 3 of these people have worked together. So if I circle them, so what if I just say they're automatically in one group? We're going to put them all together and take them out of this image right here, or this is called a graph. So if I take them away, clear, I get this. Well, if we're looking at this, you have Anna and Dan and Ed and Hal and Ira and Gia. Well, we want them to still work together. There's a slight problem now. So let's just consider over here these 3. If I put Hal and Gia with Ed, so let's say I group them because I have 6 of them, so I have to group some grouping. If I do these 3, because Hal has worked with both of them, then you immediately notice that Ira is left all by herself, because if I put her in a group with Anna and Dan, as great as they might be, she's never worked with them, or at least never successfully. That's just that I don't like that. I don't like that problem. Okay, so let's get rid of that case. And what if instead I did Hal is with Gia and Ira, and again Anna with Ed and Dan? Now notice, because Dan has worked successfully with both the other 2. Everyone in this group has had someone that they worked with. Check. In this group, both Ira and Gia have worked with Hal, so that's a good thing. So in this way, we can break them up into groups and kind of organize the information. And that is actually how we do it. Now, we have some really important things. We call these things a graph. Now, that's not like uh, any other graph you may have seen. You may have seen a sign graph or a sorry, parabola. My brain just had a total brain cramp. Sorry for that. Just you. But we do use a couple keywords. We call the dots that we had there are called vertices, or singular a vertex. Please do not say vertexes. People will get hurt. So we say vertices, and the things that we join them, we call them edges. Now, by the way, if any of you are Googling and so forth, vertices are sometimes called nodes. Sometimes instead of calling it a vertex, we call it a node. Edges are still usually called edges. It's pretty common. And vertices actually is a common thing. So let's look at another example. Let's look at this graph right here. Now, if I ask you at this graph, you'll quickly notice that, for instance, right here, V sub 1, I use a subscript. So all the V's are the vertices, and I put a subscript. So we can easily count that there are, well, 7 vertices. Similarly, I give it E sub 1 for edge 1. And this is just a random labeling. By the way, if I label them different, they could represent different things. So depending on the situation, you might want them labeled, you might want them unlabeled. There's a lot of other things. Now, let's look at just a couple things that we can take away from looking at this graph. One is, if I look right here at this edge, and it's called a loop because it starts and ends at the vertex V4. So anytime a loop, an edge starts and ends, which really means it is only touching one vertex or what we call adjacent. That's kind of an important thing. Also, I could have parallel edges. Now, I drew them so they're bending. Parallel does not mean that they are parallel, like in another sense. You thought geometrically parallel are two things that never intersect. Well, that's not what we're saying. We're parallel means they run at the same time. So parallel computing are two things working on the same problem at the same time. So two different pathways. We're running down two different paths at the same time. There's a two paths that get from V2 to V3. Both are paths, and so we call them parallel edges. And yes, we can have more than one edge between things. That's actually called a multigraph, and it is valuable and useful for different diagrams. Lastly, I'll note that this right here is a vertex hanging out all by its lonesome self. And well, it is called isolated because, well, it's all by its lonesome self and we just don't care about it. So we just leave it sitting right there like that. Now, so to go back through a couple things, the formal definition. G is a graph consists of a finite set of vertices and edges. Another way this is sometimes written is actually G equals V comma E, where you have a graph is equal to the set of ordered pair of the vertices with edges. However, the edges are ordered pairs of vertices. In other words, it's because it's a vertex that goes to a vertex. The vertices on either end of an edge are called its endpoints. And another key thing is they are said to be incident to the edge. So incident, an edge is incident to a vertex, meaning it attaches to a vertex. And two vertices are adjacent if they are connected by an edge. So those are some key things. An edge connects two things. So we talk about things as being isolated if a vertex has nothing, and vertices are adjacent while edges are incident. Yes, these are keywords. Write them down, kind of make a note. They're kind of important. So let's look at an example and understand this a little more. Here, I have a graph. I want to know the vertex set and the edge set, and then I want to give a table to show the edge endpoint functions. So let's just start with what is the vertex set and the edge set. Go ahead and pause the video. All right. So if you did that, the vertex set would be V1 would be the set V1, V2, V3, up to V6, because we have 6 vertices you see here. So that is V. The edge set of my graph, on the other hand, is E1, E2, up to E7. So again, there's sets, and I can see that simply by doing this. Now, if I did something like E1, what are so this is the edge. I made a table of the edge. And over here are the vertices it's incident to. Well, VE1 is right here, so it's incident to V1 and V2. Edge 2 is incident to V1 and V3. And we can notice that edge 3 is also the same exact incident. Now, we can keep making a similar thing like this. You notice when we do this table, at the point that we get down here, we get to edge 6, it's got only one vertex it's incident to, V5, because it is a loop. So these will all have pairs if they're normal edges, and they will be a loop if they have one single vertex in their incident set. All right. So that table, another way to look at it would be this thing right here. All right, I'm gonna go back and give you one more question. Find all the edges that are incident to V1. Okay, so let's come back to the graph so you can see that. What edges are incident to V1? In other words, what edges are attached to V1? Well, there's E1, E2, and E3. So that is the answer to that question. Now, if I ask the question of what are all the vertices that are adjacent to V1, again, all I'm asking is we come back, we start at V1, and I'm saying what vertices can I move to in just one step? Well, I can go here and I can go here. I can't get anything else, but I can get to V2 and V3. So this is the idea about we can sit here and work through it, and we can talk about what vertices are adjacent to themselves, i.e. there's a loop. Okay, well, V5 is one of the situations. V6 is in there. V4 is clearly isolated, hanging out by itself. Poor, unfortunate soul. So we have all these things that we kind of just play with. We get to know them, and we just get to know these graphs just a little bit more. All right, so let's hit one more question. Consider a graph, and I'm actually going to show you that there's a slight problem here that you can actually, I'm going to give you some information. Here's your vertex set. We got 4 vertices. We got 4 edges, and here is how we're assigning the edges. So V1 and V3 are attached to E1. V2 and V4, edge 2. V2 and V4, edge 3. Hey, this looks to me like there's going to be 2 parallel lines here, and V3 just gets edge 4. It's got a nice little loop. Now, I want you to pause the video and see if you can just graph something real quick. Can you draw something that looks like this? Go ahead and pause your video. All right, now if you go to try and draw this graph, you would end up with something that looks like this. And it turns out that these are actually the exact same drawing. Because notice that this thing right here, there's no, even though the edges cross, we really don't care about the edges crossing. I could have very easily just drawn it off to the side and it still has the same relationship. All we care about is preserving the relationships. We don't care about how they're oriented. So how we draw a picture can have, there's multiple ways we can do that. I could have also, to be honest, I could have taken the same picture right here, and instead I could have been like, okay, I'm going to get rid of this edge right here, and instead I'm going to do the edge as a big giant bendy one. There's so many ways we can draw edges. It's not fixed. It's all about the relationships. It's not about the visual of what it looks like. Make sure you understand that. Now let's look at a different picture. So we have 2 pictures here. Notice I have no labels at all. The question is, how do these 2 graphs compare? Well, if I went along and I gave them a label, so let's call this A. Let's say I call this one B and C, and call this one D and E. Well, notice that A is attached to B and C. So what if this is A? It's still attached to B and C. Okay, that's looking good. B is attached to E as well. So let's put E right here. E is attached to D, and D is attached to C. Hey, if you actually look, every single one of, so in other words, if I called this edge right here, oh, sorry, technical difficulty. If I call this edge right here, edge 1, then what I have is simply I can come along and where's my, hang on, my graph just my oh, sorry. Well, I'll just go this image. So here you can clearly see that we could label all the edges, and if we still do it, it turns out that it preserves those edges. So here's the cool part. This graph can be drawn 2 ways, either as a pentagram or as a star. And this gets into something known as the graph isomorphism problem. From my computer scientist, it's a classic computer science problem that actually is still completely open. And if you solve it, you get a bunch of money. So if any of you really want to attack this problem to have a way to do it, it's nice and easy to kind of brute force this to see if I gave you 2 graphs like we did initially. If I gave you 2 things that look like this and said, are they the same graph? Is there a way to label the vertices and edges so that they preserve all the relationships? That's a big problem, especially if I have something that has, let's say, 100 vertices in it. Because that's what we want to know if we have the same set. All right. So let's just look at some more examples of graphs to kind of just help you get a little more comfortable. So suppose for a second I'm talking about telephones, electric, or some other network. Graphs are great to visualize things and let us start looking at stuff. So for instance, this is a hub and spoke model because notice I have main hubs of San Francisco, Denver, Chicago, Los Angeles, Washington, New York, Boston, and I kind of spaced them like they would in the US. And this could be airlines. This could be how they're flowing between these places. Uh, like Chicago. So for instance, if I'm looking at this graph, this right here could be from San Francisco to Chicago. There's both a direct flight and one that goes through Denver. And they also sprout out to a couple different spots. These are all little cities. This might go up to like Portland, Oregon, then out to a couple little places or whatever. So we have all these things that we could look at, and we can start then looking at traffic that's flowing over them and things like that. Another kind of graph that's really important that kind of uses the similar sort of idea is what are called directed graphs. So we've looked at what are called undirected. So again, if you go back to the previous slide, all the edges have no direction. They have what's called a symmetric relationship, meaning they go both directions. So clearly San Francisco is related to Denver and Denver is related to San Francisco. But what if I add an arrow that gives a direction? So what if I get something that looks like this? Now this graph's a little bit harder because there's a bunch of labels on here. But for instance, notice Los Angeles Times, that's a newspaper, is an instance of a big city daily news. Big city daily news contains national news. Now, that is not national news, contains big city. It is one way, not both ways. And that's kind of the idea we have going on here. Now we can use this to answer questions like, what paper finish does the New York Times use? So we come back to our graph and we say, hey, here's the New York Times. New York Times, it goes up to Big City Daily because we just follow the flow of the chart. Big City Daily flows up to newspaper. Oh, here's paper finish, matte. Okay, so we know that it goes to matte. I could keep following it up to periodical and notice I can't come back down this direction because it's one direction. So my edges have one direction. They don't really come back the other way. So this is the idea that we get to kind of use to work through these ideas multiple times. Now, anytime I have any kind of graph, we have a key measurement called the degree of a vertex. That is the number of edges incident to it, with an edge that is a loop counted twice. So let's look at this graph. What is the degree of each and every single vertex? Well, let's start with this vertex right here. Well, clearly that vertex, the degree, again, we write this as deg v1, is 0 because it's not has nothing associated with it. What about the degree of v3? Well, I can simply count how many edges are going. I have 1, 2, 3, 4 coming into it, whereas the degree of v2 is just 2. And this information we use, we actually can make a list of these and talk about what that list of degrees looks like, and other information and so forth. But degrees do play a big role in some of the math that we do on graph theory. Now, let me end all of this by talking about one other interesting problem. So suppose this is a map. I have countries A through J. I want to color it, so to speak. I want to get some colors out there. So I want to do this as color red, but I don't want to do them all color red. So I'm going to change it up and I want to do color blue. I can only do blue. J is touching this, so I can't use, and B, so it can't use blue or red. I got to pick another color. Let's pick purple. Okay, and now for I, it can't be purple, but it could be red because it's not touching that one. And we can repeat this process over and over and over again. But the question is, how do I figure out what's the fewest colors in order to make this all work? Well, to do that, we can actually redraw this as a graph so that A is adjacent to a vertex if you go back and look at the previous slide, if they share a boundary, a border. So if they share a border, we make them adjacent. Now we're going to do the same thing. All we have to do now is quote unquote color these vertices. So I could give this color 1, I don't like that color. Let me just go back to like a black. So I can give A color 1. So I can actually give it a color. B is color 2. Now I can call it a number. And now J, it's attached to both those. It can't be 1 or 2, so it has to be, let's say, 3. And I can again return to give it color 1. And we can talk about other ways to do this. There's multiple algorithms to actually color this thing that are highly effective. But let's just look at one possible strategy. And namely, what we're going to do is we're going to assign the colors of vertices a relatively efficient manner. So focus on the uncolored vertex that has the biggest degree and is connected to other uncolored vertices. So let's come here to this graph. Which vertices have the largest degree? Well, looking at this, I can see that C has degree 5, and so does H. So I'm going to pick one of them because they're both attached to each other. So I can't pick both of them. I'm only going to pick one of them. All right. So what I can do then is I can say, let me get my colors. I'm going to give C, we'll give this a color. We'll just color C. Now, if I look around, what are the vertices that are not adjacent to C? Well, there's A is not adjacent to C, J is not adjacent to C, I is not adjacent to, and so is F. Now, of these, which ones have the biggest degree? Well, clearly J does. So we're going to keep J. But if I keep J, I can't keep A and I because both of them are adjacent to J. So I'm trying to get vertices that don't have. And so I can color all 3 of these a color. We're going to call that blue. So I color them blue. Boom. Here we made them all blue. Now that we got those blue, our next question is everything adjacent to those cannot be blue. So, and they're touching you'll notice every other vertex is touching them. So we might as well just kind of think about taking these out of the graph and looking at what's left over. So we get something that looks like this. Now we can't use blue in any of these colors. So we can color these whatever we want. Now we start asking the question again, what's the vertex of biggest degree? Well, you'll quickly notice that again, our biggest degree is still H. So H is still the biggest. Once I have H, I say, well, notice that E and A are not adjacent to H. So all 3 of these, I can actually color the same thing. So we can color them. I could also do D, but you'll notice that D has a lower degree than E. So I want to keep E in. So I always want to use if I have 2 that are touching each other, I want to take the one that's bigger degree. So if I color these 3, let's say gray, I now get it looking like this, and my color shifted. And notice the 3 that are the 4 that are remaining aren't touching each other. And so they all can be black, and that is perfectly fine. So we actually end up with a graph, if we do this, where I have 3 colors, blue, gray, and black. And we could have colored it. If you just take the same colors and transfer them to your original picture, looks like this. All right, that's graph theory in a quick intro. I hope this week you're getting a really good survey of what we're going to cover in this class. We're going to bounce around and using the keywords, definitions, all of that's important. If you're not getting something, go back over stuff. Go back over definitions. Write down key definitions, make notes, and other things. Let me know what questions you got.